Hello friends. This video is brought to you by mywayteaching.com.
It's time to examine that if two chords are of equal length, then what can be said about the size of the arc? Let AB and CD be the equal chords. To examine what is the relation between the arcs cut by AB and CD, we can cut the arcs corresponding to the chord AB and CD and superimpose them on each other. We will find that the arc CD will superimpose the arc AB completely. This shows that equal chords make congruent arcs, and we get the result that if two chords of a circle are equal, then their corresponding arcs are congruent. That is, they will lie on each other completely. The converse of this result is also true, according to which if two arcs are congruent, then their corresponding chords are equal. What is meant by angle subtended by an arc of a circle? So consider a circle with center O and consider an arc on it. Then the angle subtended by this arc PQ at the center of the circle is same as the angle subtended by the corresponding chord at the center of the circle. That is, angle POQ is the angle subtended by the arc PQ at the center O. And hence we define that the angle subtended by an arc at the center of the circle is defined to be angle subtended by the corresponding chord at the center. But what about the angle subtended by the major arc? That means this particular part of the circle. We will say major arc subtend the reflex angle POQ. In other words, when we will talk about angle subtended by an arc of a circle, we will only consider the minor arc. If PQ and RS are two congruent arcs of the circle, then they will subtend equal angles at the center. That would mean that angle POQ will be equal to angle ROS. We are now in a position to state and prove the following theorem. The angle subtended by an arc at the center is double the angle subtended by it at any point on the remaining part of the circle. We start with a circle with center O and let the arc PQ subtend angle POQ at the center. We take a point A on the remaining circumference of the circle and subtend the angle from the arc PQ at A. Then we are required to prove that angle POQ is 2 times angle PAQ. Before starting with the proof, note that we have taken PQ as the minor arc by default. But there can be a case when PQ is a semicircle or PQ is a major arc. So let us take up those cases also and then start the proof. When PQ is a semicircle, our figure will look like this. And if PQ is a major arc, then our figure looks like this. And we join AO for the proof. We extend these lines to a point B. Now look at triangle AOQ. For this triangle, angle BOQ is the exterior angle, and we know that exterior angle of a triangle is equal to the sum of the two interior opposite angles. So these two are the opposite angles. Let us write. We have angle BOQ equal to angle OAQ plus angle AQO. And this equation is true for all the cases. In triangle OAQ, we know that OA equal to OQ because they are the radii of the circle. But in a triangle, angles opposite to equal sides are equal. So that would mean that this angle and this angle will be equal. Let us substitute this second equation in 1. Then we get that angle BOQ is equal to 2 times angle OAQ. Similarly, we can consider triangle OAP. Then angle BOP is the exterior angle and it will be equal to the sum of the two interior opposite angles. And finally, following the same steps, we can get angle BOP equal to 2 times angle OAP. Now add the two equations, equation 3 and equation 4. We get angle BOP plus angle BOQ equal to 2 times angle OAQ and angle OAP. So left hand side can be written as angle POQ and the right hand side can be written as angle PAQ. Hence we have proved the required result. The only difference being that for the third case, instead of writing angle POQ after this step, we will write reflex angle POQ equal to 2 times angle PAQ for the third case. That is when PQ is a major arc. Hence we have proved that the angle subtended by an arc at the center is double the angle subtended by it at any point on the remaining part of the circle.